Can you hear me? Yes. Okay, Jonavot. Good afternoon, JSConf Budapest. Woo! I'm so excited to be here. This is so cool. But before I throw up the Who Am I slide, I would love to just start with a little short Who Am I story. It goes back to the turn of the century. My first job in technology was for a small Israeli startup called Hypernix. Doesn't exist anymore. In fact, I wasn't even hired to write any code because I didn't know how to do that back then. I was hired to work tech support all night long by myself, via chat, the graveyard shift, as we say. Now, there's Hypernix. Look at those round designs from a long time ago. So their product was actually a chat application called GUI, and it had this really fun feature where as people would type their message, the characters would sort of float up into the air and settle on the screen, and your friends could read them like that. And I remember being kind of envious of the software developers that must have developed that. I never met any of them because they all worked during the day. But I really felt like I needed to learn how can I make things move on the screen. So I did what you did, which is to send somebody to go to a bookstore and buy an actual book, and then send it to me weeks later. And since I was already awake all night long anyway, I just figured I'll just teach myself how to make things move and animate on a timeline, but then also with code. So how did that go? Well, first, I made a ball. I drew a ball. And then I made it move. And then I just did a whole lot more of that. And I kept on going, and I felt like I was now in this new world of joy and creativity. And it was so much fun. And back then, companies would actually pay me to do that kind of thing, the thing that I was quickly growing to love. And I can honestly tell you, those were some of the most exciting, lonely nights of my life. So, I just want to say that if any of you can remember that moment when you first felt that spark of joy related to your work, or maybe that moment when you realized that you had a passion for building cool stuff and it was now part of your DNA, I hope that you honor that moment. I hope it motivates you ongoing. I hope you'll inspire other people, and I hope you'll come up and meet me and tell me all about it before the conference ends. All right, so my name is Kevin Maes, and just like the many versions of ECMAScript have evolved, so has my career. I've done product development, I've done project management, people management, consulting, you name it. But for the last couple of years, I've been working with this awesome team at Stately, building visual diagramming tools. Visual diagramming tools for individual developers or teams just like yours, based on an open source state machine library called XState, which was created by David Khorshid, who gave that awesome talk yesterday about the actor model. OK, so you're all caught up to present day. And I live not that far away from here in Malaga, Spain. And every day, I wake up to the sights and sounds of all these cool birds swarming around. It's very mesmerizing. It's lovely. It reminds me a little bit of those old animations from back when. And it also got me curious about what kind of algorithms are there that were inspired by nature. And so that's how I stumbled upon GAs, or genetic algorithms. We'll call them GAs. And these are not new at all. They're actually part of a field called evolutionary computation, which itself is a branch of artificial intelligence. Very popular today, right? So please join me as we go back even further in time to witness the birth of GAs. OK. So we begin in an era where computer scientists all had black and white headshots. Meet Lawrence Fogel. OK, Lawrence Fogel. Now, in the 1960s, he had this idea for genetic programming, and he wanted to basically simulate the process of evolution using state machines. Now, state machines, they're just a way to model behavior transitioning from one state to another because of events. We've heard about that already at this conference. Now, Fogel's approach was to actually use a whole population, and that's a key word, of finite state machines that could adapt and optimize their behavior over successive generations, OK? And these generations, they would actually allow them to mutate along the way. So he used these principles to predict things like time series data, for example, stock prices or maybe weather, all based on past values. Now, shortly after that, a professor from the University of Michigan named John Holland entered the scene, and he built upon these ideas to create genetic algorithms. Now, those two disciplines are joined by a couple of others, but they all make up the most popular algorithms of the evolutionary computation field. But out of all those, genetic algorithms are actually the most popular and widely used. I do want to go back for a second to John Holland. So before he became the father of genetic algorithms, he got a physics degree from MIT. He got a master's degree in math from the University of Michigan. He actually got the very first doctorate in computer science from the University of Michigan. And then he went on to teach as a professor in 3 different departments, okay? 1, computer science, obviously. 2, electrical engineering, okay. And 3, you guessed it. Karen Kenzie, if you're here, you can guess it. Psychology. All right, so I think it's safe to say that John Holland was a highly evolved human being. But his real breakthrough came when he looked beyond machines, okay, and he actually looked towards natural systems. And he was inspired by Charles Darwin's theory of evolution by natural selection. And he wanted to see in his work, could the processes that are biological processes like selection and crossover mutation be applied to systems that are artificial in order to make them more adaptive and intelligent. So in 1975, he wrote his groundbreaking work where he actually detailed the theory and the practice of genetic algorithms. And he combined all these things like biology and math and computer science all together in order to solve optimization problems. Okay, why do we need any of this? Well, the main purpose of genetic algorithms is to arrive at a desired behavior, some sort of optimal design, or to solve complex search problems. So imagine that you have a problem, and you're given an infinite number of tries to solve this in a random way. Well, eventually you might actually solve that, but it's going to obviously take a very long time. So GAs use the concept of natural selection and survival of the fittest to basically super speed up that process for you to come to a solution. So what sort of problems can we solve here? Well, they can be used to design efficient network topologies. So for example, you've probably heard of the traveling salesperson problem. Companies like UPS have actually used GAs to optimize their delivery routes, making them much more efficient and cheaper. There's also things like automated software testing or model-based testing, and GAs can be used to not only generate the tests, but also to even narrow them down so that what remains are the more effective tests. Of course, there's game strategies, games like chess and Go. These can also be evolved with GAs. And educational institutions use these to solve complex scheduling problems, something called the conflict-free timetable. Now, there are also applications in hardware. Okay, so for example, in 2006, NASA flew the Space Technology 5 mission, known as ST5, and the purpose of that mission was to basically flight test innovative technologies in space to see how they do. They launched 3 satellites, and each one of them was equipped with technologies such as low-power batteries, thermal regulation, propulsion systems, and also communication devices like satellites. So not satellites, like antennas for the satellites. So designing antennas at the time was actually very time-consuming and labor-intensive. So what did they do? ST5 included what is known as an evolved antenna. And an evolved antenna is basically an antenna that was designed by a GA run on a supercomputer. All right. It started with a simple antenna shape, and then it started to add and modify that shape in a semi-random manner. And all of these different iterations were judged on their fulfillment of design criteria and given a numerical score. So NASA is building this big space satellite, right? And obviously, it's much easier to iterate thousands of times on a design using a supercomputer before finally committing the resources and everything to manufacture and assemble this great satellite antenna. So what did the final product look like? Well, it looks like a bent paper clip, okay? But this tiny, weird-looking communication antenna actually featured lower power and much faster build time. And it was twice as efficient as any manually designed antenna was. Now, NASA still uses these evolved antennas because their mission requirements change frequently. And anything that's evolved from a GA, like an evolved antenna, is basically cheaper and better able to adapt to all of those changes, all thanks to GAs. So how does this work? Well, there are several steps involved in a GA, and we can go through those quickly. The first is population initialization, and that only happens once at the start. And we'll look into these more detail. Then there's evaluation, also known as evaluation and fitness. Okay, then there is selection, and then crossover, and mutation. And then those last four are actually run maybe hundreds or even thousands of times over and over again. And each of those iterations is considered a generation. And each of those generations has its own new population. OK. So the GA is going to manage this sizable population of individuals, we can call them. They're referred to other things, too. But each one of those individuals can contain a potential solution to the problem. And that solution is encoded in its sort of DNA, right? Now, you can think of that as sort of a representation or possibly a serialization of the characteristics of that individual or perhaps its solution. It's also important to note that in population initialization, that's where we first establish a wide range of variety for the population. Oh, my goodness. Hold on 1 second. I don't know how I exited that. Now I can't get it back. Oh, no, it's up here. Yeah. Oop.
Computers.
Yeah. Oh, notes. OK.
Yay!
Yeah. Cool. OK. And then I got to go back up here and full screen you. All right. OK, well, so. All right. I don't know about the clicker. Maybe I'll just use this thing. OK. OK, so where were we? Oh, yeah, so evaluation and fitness. Whew. OK, evaluation is perhaps the longest stage. And here we're going to let the individuals actually attempt to solve the problem. And that might include interacting with their environment. Now, the most important part of this stage, though, is the fitness evaluation I mentioned. So using a fitness function, we have the ability to score and to reward and to punish these individuals for their behavior and how well they do. And every one of those individuals will be assigned a fitness score. OK, in selection, only a certain subset of the population will be selected based on their fitness to serve as parents of the next generation. And this gets interesting because there are different ways that we can go about selecting for fitness. One of the most common is called roulette wheel selection. And in this method, basically the likelihood of being selected is directly proportionate to your fitness score. So for example, if we add up all the fitness scores, we get a wheel or a pie or what have you. And obviously, the individuals with the higher score are getting a disproportionate amount of that pie. So then if we randomly select some degrees on that pie or some number, then they will have a higher chance of getting picked. But because it's still random, it is still possible to pick lower performers, and that's still good for variety. We typically want maybe 30 to 50% of the population to serve as the parents for the next generation. OK, crossover involves mating parents. And one thing we know for sure is we do want to maintain the same population size from generation to generation. Now, how we combine DNA is interesting. It depends on the nature of the DNA, right? So if DNA made up of, like, say, chromosomes are just values, numeric values, perhaps we can average them. But if it's something more complicated, then we might actually have to decide, oh, we're going to pick from one parent, or we're going to pick from another parent. Mutation is a place where we have a chance to keep that variety in the population, which is very important because we need variation to avoid something called reaching local optima. And local optima is simply when the individuals kind of think that they've come across the best solution, but only within a local area or time period. But in reality, it is not the global optimum, which is much closer to the true solution to the problem. So chromosomes in the DNA, we can choose to have them be mutated according to a mutation rate. And of course, each one could be mutated according to some sort of amount, a mutation amount. All right. Now that we've created the generation, we want to return to evaluation and rinse and repeat and see how the new population handles all of that. So I mentioned that GAs are used to solve complex optimization search problems. But I'm kind of a simple guy, and so I decided to just try this out with some creative coding. So let's take a look at some of that. OK, so we're going to go very quickly. So we've actually seen a little bit of Canvas yesterday in Francisca's talk, but it's very easy. Basically, you put a tag on the HTML page, and then you get a reference to it by its ID, and then you set a context, which is either 2D or WebGL for 3D. We're interested in 2D today. OK, so this is the first example. And basically, it's a GA in JavaScript using Canvas. And the goal is simply to have this red circle in the middle, and then to have a bunch of randomly placed and sized circles around, all converge as a population to match that circle. Now, I'm going to be very quickly going through code. Might even have to skip some things here. But it's all on GitHub, so don't worry. You can just see it whenever you want. OK, so in the population initialization phase, we talked about we basically create a loop up to the population size, where we're going to create a circle with random size and position. We add it to an array. The draw function is super important in any kind of Canvas or creative coding project like that. So we need to loop over the population, and we need to draw each one of the circles, of course. I gave them a little bit of red color so that if they actually match the target, then they'll look a little bit more like the target. And for now, each circle has a gray outline. But let's see, if we remove that stroke, then it actually looks more blended and kind of looks like a particle effect or smoke, and it's nice. So we also draw the red target circle on the top, so you can see that as a reference. OK, so now if we speed up the frame rate to about 10 frames per second, then we can see that we've already found our first match in generation 7 there. OK, now with evaluation, basically we want to map over the population here, and then we want to kind of call some method to calculate a fitness score. And so in that fitness score, this is a very simple example, so we're really just comparing them to the target. We're saying, are you the same size, and are you in the same position? And then we're giving them a score based on that. In this case, it's sort of normalized from 0 to 1, 1 being perfect match. OK, now, for example, if we were to disregard distance, we can actually have this concept of sort of like weighted fitness. So this is an example where if you disregard the distance, then quickly match on size, but not on position. And conversely, if we disregard the size, then we can match only on position. All right, so here in selection, we're going to choose the total number of parents, and we're going to use the roulette wheel selection to get to each one. It might be easier if I just look at the code. OK, so in the roulette wheel selection, we need to add up the total fitness scores. And then what we're doing is we're picking a random number, and we're sort of like cycling down through the population until it bottoms out at 0. And whatever it lands on, that's the individual that we'll choose to be a parent. OK, and then in crossover, we need to randomly select from that pool of parents to pick 2 different parents. And they both have to be random on their own. They can't be the same parent, of course. And here we're producing a child, which is just the crossing over, or the averaging of the x, y, and the radius values. This is so hard. OK, in the mutate function, this is where we possibly mutate every individual. And you see we're basically cloning that individual, and we're calling the mutate value, which is sort of like maybe mutate value, for each one of the x, y, radius properties. And then in that, if we expand the mutate value function, then you'll see that we pick a random number. And if it is within the mutation rate value, then we will apply a mutation according to the mutation amount. Yeah, so otherwise, we just return the value as is. So again, very, very fast here. Sorry about that. OK, so in the final run, we can see, actually, that we find a match in generation 7, and we actually find they all match. This is just looping. They all match within 1,000 generations. So simple example, but we use the GA to basically rain in hundreds of random circles to converge on a single target circle. OK. OK, next example here is a bunch of particles. OK, so these particles are going to be set about in a very random way on the left side, and the goal is very simple, just to basically get them off to the right side and off of the canvas. All right, so if you see that this all starts out in a very chaotic mess, we have random particles with random speeds, random positions, going off in random directions, and none of them can actually stay on the canvas. But actually, 5% of them did manage to make it to the goal. So that's actually interesting on the first run, or first generation. OK. Now, here you start to see something else. You see there's some little arc lines. I know the contrast is not great. There's some sort of little arc lines. That's kind of like a rudimentary radar system that I'm gifting them. It doesn't work very well, but it basically is done by projecting out a couple of rays and linking the lines with arcs. And that is so that they can have some hope of perhaps avoiding the walls or the boundaries of this canvas so that they could stay on long enough to make it to the far right. All right. And then right now, you also see there's some notion of color. All that is that they start out white, but as their lifespan approaches that of the average lifespan of their two parents, then it comes from white into yellow. And then once it starts to exceed that, it actually goes even deeper to sort of like an orange. OK, so now we're starting to see some directed motion. Oh, I can look right here. We're starting to see some directed motion, and I think it'd be a good time to talk about the fitness function, because it looks like I might have time for that. So basically, we want to reward any of the particles that actually make it off of the right side of the canvas. But also, even if they don't, then perhaps they've managed to repel the wall successfully. So we can also track that and reward for that. If they do die, and many of them are still dying, then it's at least worth seeing, well, how far did they make it towards the goal? Yeah, it's always root for the underdog, OK? Thank you. All right, and you can see that we're actually now over 50%, and we are climbing steadily, right? OK, so yesterday in David Krasheed's talk, he talked about agents, and he talked about how they are able to observe their environment, they're able to make changes, or make even decisions maybe, and to learn over time. So this canvas is actually divided into multiple zones, and those zones are, let's say, something that those particles can kind of identify and say, oh, I've been here. Oh, where am I going to go that I haven't been before? It's kind of like when you're looking for your car in the parking lot, and you've been to A, and you can't find it. You've got to go to B, and D, and C, obviously. OK, so now at this point, we're starting to see some kind of what looks like group motion going to the right, which is nice. And we're over 93.8%. So let's see. Here we go. OK, all right. And it looks like there's a couple failing. But I think we might reach 100% of the next generation, right? What do you think? Oh, looking good, looking good. Oh, so close. OK, all right. Well, let's give it one more try here. Whoa, woo! We did it. Or rather, they did it. They did it. So in summary, we used the mechanics of the genetic algorithm to basically take what was fast, random, chaotic, motion at the beginning and turned it into something that was slower and steady, more deliberate, and more cohesive as a group towards a positional goal. So yeah, thank you very much for that. Oh, good, I'm on time. So. OK, so both of these examples, as I mentioned, they're on GitHub, and I'm going to share out this deck soon, so you'll get that too. One sec. OK. OK. All right, so let's move on to some other things. So I, thought about some general tips. I mean, this is not as deep as Francesca's talk, but I think that some things you can do when you're working with Canvas is, remember to clear the canvas between your animation loop cycle so you don't have any artifacts that remain. Also, there's something called request animation frame, and I definitely recommend that you use that in order to let the browser maximize the refresh rate of the animation. You can look it up. And then I'm always just amazed at how fast animations actually run in Canvas, so that's cool. One other thing is that we've talked a little bit or heard some talk about like functional programming and in JavaScript, as much as that is, and I like that, but I actually find when I work with particles, it is kind of nice to just go back to, like, let's say, classes in JavaScript. And the main reason is because each one of those instances can maintain their notion of their own state in terms of their position, their size, their animation properties, and you don't have to like look it all up all the time. But it's just a preference. And the other thing is you could create a class for, let's say, the population, and that population could have handy methods that deal with the entire population, such as assign fitness or select parents, anything that iterates over everything. OK. P5.js, again, another shout out. I mean, sometimes if you want to get up and running quickly, this is a great way to do it. It's a JavaScript library that's wrapping Canvas, inspired by the processing language, which, as we heard, is used for generative art. And Francisca has just such a great talk about that. So there's a bunch of benefits here, and there's also the free-to-use playground as well. OK. So these experiments have just been kind of whimsical, but I feel like I've learned a little bit about how GAs work. So for example, population size is super important. If it's too small, you're just not going to get the required diversity you need to solve the problem. If it's too large, then you actually may just be doing a lot of extra work, or it could just take a very long time to converge on some consensus or to find a solution. Fitness, I would say you just need to experiment, experiment, experiment. This is where you can be super creative about tweaking the fitness according to the requirements or this problem you're trying to solve. Now, selection, there are other selection methods, things like tournament selection or truncation or rank-based selection, and all of those are designed to basically change what's known as the selection pressure, which is the intensity in which the higher performing individuals get selected for the next to be parents. And then for mutation, you have to avoid that premature convergence. And that's something where you can also experiment on a per chromosome basis, basically tweak the mutation rate, tweak the mutation amount, et cetera. OK, can the GA help us? So as you seek to tackle some of the problems that you deal with on a daily basis, there might be ways that GAs can help you. And these are just some ideas. Some of these I think are being worked on, but others are just kind of things, food for thought. But I think that at the very least, knowing how GAs work and how they've been applied in software and in hardware could maybe give you some clues as to how you can better iterate on some of the projects that you have. OK, in terms of resources, lots of academic papers. Oh my gosh, there's so many PDFs. But some of them are very interesting, and you can look for those. And there's also tons of great experiments about this on YouTube. But I have to give a shout out to the coding train. Who knows about the coding train? Woo woo! OK, I heard a woo woo. So Daniel Schiffman creates the coding train, and it's just brilliant. I mean, he has an entire 5-6 video series dedicated to genetic algorithms, where he deep dives into all that. And he also has basically videos about everything under the sun related to creative coding. So another thing that I'm super excited about is about 12 years ago, he came out with a book called The Nature of Code, and that was for the processing language. And it details like all these ways that you can code and simulate natural systems or natural behavior. So there's actually a new version that's for JavaScript, okay, coming out in September. And I really look forward to that. So I recommend keep an eye out for that. I admit I do still buy hardcover books today because you can take them to the beach and read them there. OK, so speaking of important historical events in computer science, 10 years ago, this movie came out, The Edge of Tomorrow, right? Anybody seen that? Yeah. OK, all right, so for those who haven't, it's the action-packed Groundhog Day with Tom Cruise and Emily Blunt. I don't know if you know this, though, but it actually has a tagline, and that tagline was, live, die, repeat. And I think that, to me, that reminds me a lot about what we've been seeing today with the genetic algorithms. Right? Now, so in that movie, Tom Cruise, protagonist, he's repeatedly killed off over and over again. He's fighting in this harsh environment, and he's battling for his life and the life of humanity against these crazy aliens. And every time he dies, he ends up right back where he started and doing it all over again, except that he retains the knowledge of his previous lives, and he's able to leverage or take advantage of his successes and avoid his previous failures to become a better survivor. Now, we as humanity, we pass down knowledge, right, from generation to another generation, and then to the next generation. And in fact, some of these genetic algorithm ideas, they've already been passed down to us through multiple generations. By the way, that is supposedly the title of a sequel that's going to maybe come out someday. I don't know, we'll see. But until then, I really hope that you'll have some fun with genetic algorithms and also creative coding. And remember, as long as we continue to find a way to come together just like this, to share our knowledge and our experience and our passions, then together, we as a population can achieve any goal. Thank you so much. Thank you.